This topic we are going to learn Cayley-Hamilton theorem. Statement is every square matrix satisfies its characteristic polynomial. This one is our statement. Every square matrix satisfies its characteristic polynomial. That is, for any n by n square matrix A, suppose its characteristic polynomial is denoted by Ca of lambda. C for characteristic polynomial, A is matrix A, lambda is variable, determinant of A minus lambda I. Now determinant of A minus lambda I or determinant of lambda I minus A, both are same, or determinant of lambda I minus A, both are same. Difference is of only minus sign, so that we here adjust minus 1 raised to n. Now note, for 2 by 2 matrix we get characteristic polynomial in lambda square. For 3 by 3 matrix we get characteristic polynomial with highest degree 3, that is from lambda 3. So for any n by n matrix we get characteristic polynomial in lambda raised to n. Okay, so highest degree polynomial is n. Now square matrix satisfies its characteristic polynomial means in Ca of lambda we replace this lambda by a. So instead of lambda we put out a. So here in this polynomial we replace all places of lambda by a. So we get minus 1 raised to n, a1a, a2 a square up to a n minus 1, a raised to n minus 1 and a raised to n. Now note that a is a matrix, so a1 a is matrix, a2 a square is matrix, this is matrix, but here only a naught is in some value, some scalar value. So to create this term also matrix, we multiply a naught by I. Okay, so now our claim is Ca of A should be 0. Proof: as we have learned that A inverse is 1 upon determinant of A, we all know this. A inverse is 1 upon determinant of A into adjoint of A. So if I determinant of A, if I replace determinant of A by A inverse, means A inverse go here, determinant of A go here. So I will get determinant of A is equal to 1 upon A inverse into adjoint of A. Similarly here A inverse is matrix, adjoint of A is matrix, but this side determinant of A is some value. To create this as a matrix, I multiply this by I, identity matrix. Okay, if I adjust the term A 1 upon A inverse is A into adjoint of A is nothing but determinant of A into I. Now we replace this A by A minus lambda. So instead of A we write here A minus lambda. Adjoint of A is written as adjoint of A minus lambda. Determinant of A is written as determinant of A minus lambda. I is as it is. This is equation star. Now note that entries of adjoint matrix A are nothing but cofactors of A. Hence entries of adjoint of A are determinant of, what are cofactor? It is determinant of n minus 1 square submatrices of A. That is, adjoint of A is a matrix whose entries are polynomials in lambda of degree at most n minus 1. Now as adjoint matrix is a matrix with every element is obtained by cofactors of A. Cofactors of A are determinant of n minus 1 square submatrices of A. So obviously adjoint of A is a polynomial of degree at most n minus 1. Maximum degree is n minus 1. Okay, so now here we get adjoint of a minus lambda is, now I choose, instead of a naught I choose some different scalar quantity. So I take here b naught, b1 lambda, b2 lambda square up to bn minus 1 lambda raised to n minus 1. Okay, now from equation star we have, now a minus lambda is as it is, a minus lambda. Adjoint of a minus lambda is replaced by b naught plus b1 lambda plus b2 lambda square up to bn minus 1 lambda raised to n minus 1. Now determinant of a minus lambda, determinant of a minus lambda is minus 1 raised to n into a naught plus up to lambda raised to n. Determinant of a minus lambda is here. Determinant of a minus lambda is nothing but characteristic polynomial. So I replace it by characteristic polynomial into I. Now if I do matrix multiplication, I will get here a into b naught, a into b1 lambda, a into b2 lambda square. Similarly up to a bn minus 1 lambda raised to n minus 1. Similarly if I multiply lambda I to b naught, lambda I to b1 lambda, lambda I to b2 lambda square, lambda I to bn minus 1 lambda raised to n minus 1. I collect these all terms in variable lambda. So first constant term is a b naught. You can see here a b naught. Now I search terms for lambda. Now a into b1 lambda. Okay, so here a b1, then minus lambda I into b1 is nothing but minus b naught I lambda. Okay, so this is nothing but only b naught lambda. Similarly for lambda square, a b2 lambda square, so here I get a b2, then lambda I into b1 lambda is nothing but lambda common, so minus b1. Similarly I collect all these terms in lambda square, lambda raised to n minus 1, lambda raised to n. Now this is our left side. Now for right side, similarly minus 1 raised to n into a naught into this term a naught into I, minus 1 raised to n a1 lambda into I, so minus 1 raised to n a1 into I into lambda. As on left side I collect coefficients in lambda square. Similarly on right side I also collect coefficients in I, lambda square, lambda raised to n minus 1 and lambda. Now if I equate coefficients on both sides, I will get, obviously this is constant, this constant will equate with this term, so I get a b naught is equal to minus 1 raised to n a naught I. Now here a b1 b naught, a b1 minus b naught into lambda is nothing but minus 1 raised to n a1 I into lambda. Now both side lambda is common, it get cancelled, so I will get a b1 minus b naught, a b1 minus b naught equal to minus 1 raised to n a1 I. Similarly a b2 minus b1, a b2 minus b1 is minus 1 raised to n a2 I minus 1 raised to a2 I for lambda raised to n minus 1. Similarly in this way for last two terms, a b1 minus b n minus 2 lambda raised to n minus 1 is here minus 1 raised to n a n minus 1 into I, lambda raised to n minus 1, lambda raised to n minus 1, lambda raised to n minus 1 get cancelled, and I will get a b1 minus b n minus 2 is equal to minus 1 raised to n a n minus 1 into I. For the last term, minus b n minus 1 into lambda raised to n is minus 1 raised to I into lambda raised to n. Lambda raised to n, lambda raised to n get cancelled. So I will get minus minus bn minus 1 is equal to minus 1 raised to I. Now I multiply these equations on the left by a square, a raised to n minus 1 and a raised to n respectively. Means I will multiply this first equation by I. I will multiply this first equation by I, second equation by a, third equation by a square respectively. Similarly, this equation by a raised to n minus 1 and this equation by a raised to n. So my first equation will be as it as it is, because first equation is multiplied by I, so it is same first. So for second equation I multiply this equation by a, so I will get instead of b naught minus b naught plus a b1 multiplied by a, I will get a minus a b naught plus a square b1. Similarly on this side, minus 1 raised to n a1 into a into I, so it is a. This is our second equation. Now for third equation I multiplied it by, this is my third equation, I multiply it by a square, so I will get minus b1 a square, so minus b1 a square, a cube b2 is equal to minus 1 raised to n a2 a square minus 1 raised to n a2 a square. Similarly I will get all these equations. Now make partition. Check that on left side, if I add all the terms on the left side, I will get a b naught minus a b naught, this term will cancel. A square b1 minus a square b1, this term will cancel. Similarly in this way, here for the previous one term, this term and this term will cancel. A raised to n bn minus 1 and a minus a raised to n bn minus 1 also get cancel. So on left side I will get 0. So sum of all these terms is 0, because a b naught and minus a b naught cancel. Similarly if we do addition, all terms get cancelled. Okay, and on right side, minus 1 raised to n is common in all, so I will take it common. Next terms are a naught I write down here a naught I, a1a is here, a2a square is here. Similarly a n minus 1 a raised to n minus 1 and a raised to n is here. But this is nothing but this whole equation, is nothing but CA of A, as we see here. This is nothing but CA of A. I want CA of A is equal to 0. This is my claim. Now I get here CA of A is equal to 0. So I can say here that every square matrix satisfies its own characteristic equation. So this is proof of Cayley-Hamilton theorem. We will see more problems regarding this in our solved section. Thank you.